Swayam Prabha. Digital India. Educated India.
Good morning, gentlemen. In this lecture, let's talk about the development of finite element equations of 2D problems with one variable. And in particular, they look like this one. So a typical example of so this is the Poisson's equation which I'm taking, wherein it's a second order partial differential equation. And this is the domain. So this, we have been seeing it again and again, where phi is just one variable and then a function of xy. And this is a heat connection. So with respect to the heat connection, this is the Poisson's equation. Together with the boundary condition, of course. So boundary conditions are, this is a heat conduction problem. Where phi is a function of xy, and here we call it as temperature. The variable is temperature, and it's a second order differential equation, and K is the conductivity, and Q is the heat generated or heat distributed heat source. It's a distributed heat source in omega. And then the boundary conditions are K is the conductivity, and the boundary conditions are so the heat flux boundary condition here on gamma Q, I will write it here. Phi is equal to phi bar on gamma phi okay. So here this is heat flux leaving, and that's what's given here. Okay, so this is a typical heat conduction problem which can also be applied to many other applications, such as it can also be applied to torsion of a non-circular cross-section, or even some flow in porous media. And then we also have, and many other problems which we come across. And here we take the heat conduction because we are more familiar with the heat conduction, as well as the boundary conditions are quite familiar to us. So this is the 2D problem, and then let us see how we can apply it to in the context of finite element analysis. So in the finite element analysis, so the domain is divided in the finite element analysis. The domain is divided into several subdomains. Omega 1. So we have into several subdomains here. A general subdomain is omega E. And in the finite element analysis, the main thing is that the phi, the approximation, phi is piecewise defined. This is the fundamental of the finite element analysis. Piecewise defined. And that means that phi is equal to phi E in the subdomain omega E. So omega E is, the subdomains obviously are called the elements. Okay. So these are called elements. So as you can see here, by the time you come to the TD, the subdomains may be of different shapes. It can be a shape like this one, maybe quadrilaterals or even slightly curved shape also. So they are all connected, interconnected at points known as nodes. Okay, so these elements are very crucial to us, and then these elements may be from the simplest shape, the triangle, all the way to rectangular elements or quadrilateral elements, or even curved elements with several nodes. Okay, so that is of different shapes, and depending upon the shape and depending upon the requirement, we may have different approximations. So one of the simplest element here is a triangle. Simplest element is triangle. So if you have any domain like this one, so it is divided Okay, so you can see that triangle have three sides with three nodes, and they need not be of the same size or of the same orientation. They can be of different, but basically they are, at this moment, they are triangles with the three nodes, three vertices. The advantage of this triangular mesh is that any complex domain can be subdivided into a conglomeration or a union of the triangles. So one important factor here I can point out right now is that any complex shape here can be subdivided into elements, but however there's to any degree of accuracy. So what do we mean by accuracy? So when you talk about these things, so there are, each element has three sides, three straight sides, and particularly when you talk about the boundary, so there is a small zone here, which is not represented by any element. So this is some kind of error, and of course we will talk about this error a little later. So this is one of the errors where the geometry cannot be fully represented by the mesh we take. So there are some gaps and may even be some overlaps. So for example here, so the triangle is overshooting the actual domain, and so it's possible that the triangular mesh will not represent the complex shape fully well. But however, there is one thing which you can observe here. So this unrepresented portion, which is the error, can be made as small as possible by taking more number of elements. So what may more number of smaller elements? For example, here, if I take two elements here of smaller size, so you can see this unrepresented portion here, small one, which I'm marking with the brown one, is becoming smaller. So that way, it's the error can be reduced and the complex shape can be represented to any amount of accuracy. So that is the advantage of this triangular element. So triangular mesh by, I'll write it here, by taking smaller triangle elements, we can represent complex shapes to any amount of accuracy. So this is a very important observation. This is not true if you have some other type of mesh, such as rectangular mesh. If you have rectangular mesh, so they are very, very rigid. So they have to be, the sides have to be horizontal and vertical. So the error cannot be reduced so easily. So this is the now so convenient. So advantages for the element which we use for the complex shapes. Okay, so that's one observation. So we are going to concentrate right now on the triangular mesh. So the triangular mesh now, so that means that we have a general element like this one, omega E. So the general element so it has three nodes here. So let us say, so the triangle, let the triangle has three vertices here, and which are nodes, three nodes, which we call for the moment and say ijk in general. So this is I, J, K. Please don't get confused this K with this K here. This K there is conductivity matrix. So this is I, J, K, right? So this is the triangle with 3 nodes. There is also another consideration which we just going to talk about. So now we have to see what kind of approximation which we require here. So the approximation here, so if you talk, so what is the approximation which we want to use for this element phi e? So it depends upon what type of weighted residual statement you have here. So we have this weighted residual statement. Weighted residual statement which we have here. To start with, we have this. This is one term, and this is the residual in the domain omega. And phi, of course, obviously phi, we'll write it as phi hat. So, and then we also have the residual. So this we discussed when we talked about the weak form. So this is a repetition of that. But for the sake of completeness here, we require these statements here. So this is the residual due to the boundary condition on heat flux gamma Q. And this is, now we went through the whole steps. So this is where we take this term into consideration. So going through integration by parts and so on. So what we have here is that this is the weak form of the residual, right? And then, of course, we have okay. So having this now here, obviously there are other conditions here that when we take this weighting function Wi, so if you want to make this 0, so we'll make this 0 by taking Wi equal to 0 on gamma phi, and of course the other gamma phi, gamma q has been cancelled here, and then we have this here. Okay, so the next step is that by looking at this phi hat, so this is having the first derivative here. So that means that when you assume it as piecewise defined functions, So phi hat should be should be continuous such that the derivatives exist. They are unique and exist within the element. So phi e, so when you take the derivatives, then they should exist. And the other one is that if they have discontinuity, so dou phi and dou x may have finite discontinuities. So this is the at element boundary. So this is very important. So that means that the derivative may have finite discontinuities at the element boundaries. So such function is called C0 continuous function. The function is continuous and it may lead to some discontinuity in the derivatives, but then these discontinuities are finite in nature. So essentially, the integration can be done of the derivative. Though what we mean by that is that at the element boundary, so there is non-uniqueness of the function, and so but still we can regularize the function by joining it smoothly, and then we can go ahead with the integration, and in the limit it happens to be the integration over each element. So that is the important part here. So as far as the phi e is concerned, so we need at least it should be derivable within the element, and then it may have discontinuity at the element boundary, but a finite discontinuity, so which we call as C0 continuity. So therefore, so we choose a minimum of linear function. So what we mean by this is that the element now here for the triangle, so now at least it should be, basically you should have at least the first three terms of the expression. So a plus bx plus cy, so that this is differentiable within the element. Of course, it will give you, if you differentiate it with x, it will give you b. If you differentiate it with y, it will give you c. So this is what the function is. So let's now go further. What are those constants ABC? So let's try to find out what is that phi e. So we have a triangle here, I, J, K, so what we have here is that phi e within the element is a plus bx plus with three coefficients a, b, c. If you recall, so to ensure C0 continuity, so we would like to replace or rewrite this ABC in terms of the nodal values. So we like to rewrite ABC in terms of nodal values. So here say phi I, phi j, phi k. So this is phi I, phi j, phi k are the three nodes. So this is another very important observation here, is that when we write this a plus bx plus cy, so you can continue to write any number of terms. You can, that's what we are going to do later. So if you want more terms, so we can continue to write. Here we write only with three constants, it's good enough. And then those ABC will now be replaced by the phi I, phi j, phi k. So how do we rewrite this a plus bx plus cy ABC in terms of phi I, phi j? So this is, observe that phi is equal to phi I, phi at xi yi is, we call it as phi I. So this is nothing but a plus bxi plus cyi, right? So similarly, phi at xj yj is, we call as phi j, and this is a plus bxj cyj, right? So similarly, we have phi at xk yk, which we call as phi k, is nothing but a plus bxk plus cyk, right? So using these three equations, we should be able to express ABC in terms of phi I, phi j, phi k. So which we can write it concisely in matrix form. So how we write is that phi I, phi j, phi k is equal to okay. So this is we are writing this. So this is the matrix of coordinates, and this is ABC. So that means that now we can find out, if you call this as some matrix C, coefficient matrix here, please don't get confused this C with this C. So we can find out just to wrap it up. So that means that now, so this phi E, now we can write it as 1 using the matrix So the first one here, a plus bx plus cy, can also be written in this fashion, so that we can, this is the row matrix here, ABC is nothing but C inverse So this is a C inverse is just a 3 by 3 matrix multiplying with 1xy. So let us say that, so what will be that? So this is a coefficients matrix multiplying the terms 1xy. So finally it will turn out to be so I will explain what is this Ni, Nj, Nk will be, or we can write this one. So finally, so the approximation function within the element can be written as Ni xy. So this whole thing now we'll expand it back to the longhand form. So it is Ni times phi I, Nj times phi j, Nk times phi k. So that means that originally when we started off with this one as a plus bx plus cy, now it's being expressed as functions Ni times phi I, Nj times phi j, Nk times phi k. So that means that now the ABC are rewritten in some other form, phi I, phi j, phi k. So these are the new coefficients. So we'll start from here in the next class. So for the present, so we'll stop here and we'll continue in the next lecture. Okay, bye.